do, but what I will do, because I have to. All right. Online people, you're going to get to hear my booming voice the entire time. Yay. So, let's make certain this is actually working as well. If not, this will be doubly devastating. Well, let's hope this whole system's not messed up. It's a good chance it's mine. Uploaded the solutions to the quiz. So that's there. You all do have the circuits and current quiz due by the end of this week. I will actually give you all a little bit longer time on that because I know the test is this week, so I'll send out an announcement. But basically my plan is I'll extend this quiz that we currently have. So you all have quiz 5, current and resistors. Yes, this stuff is on the test. P equals IV, V equals IR. That's basically all that we covered there that was important. Yes, this is on the test. I will extend it till next Tuesday. I will extend the time on that because that way you all can focus on studying for the test and not worry about this quiz as well. Yes, sir.
DC circuits.
DC circuits will not be on this test. I haven't covered anything about it. DC circuits, I know it showed up in the problem set 1. I apologize. The previous problems, the problem set 1, had DC circuits written at the bottom. That is going to be on test 2. Test 2 will be DC circuits, which is why the quiz on it isn't until March 4th, which is quite a while. So, let me just remind you all. So, our test is this Thursday, which we hopefully all know. Reminder to you all, you're going to get the test. There it is. It has 25 multiple choice. It has 3 free response. You will only pick 2 out of the 3 free response to answer. There'll be a little checkbox next to it. I need you to, and I'm going to remind everyone this on the day of the test as well, I need you to put your name on both the front of the paper, and when you all get here, you will tear off the back paper, and that will be the Scantron that you're going to use. I'm not making you all get Scantrons. I'm giving you the Scantron. Why? I can scan these with my phone, which is really nice because then I can get the grades in quicker and I can get kind of immediate feedback on what problems you all did well on and which problems you didn't do well on. The grading is going to be, I will be able to post these probably within a day or 2. I'll be able to scan all 220 tests and I'll be able to post how you all did on the multiple choice. The free response is going to take a hot minute to grade. I told the grader, please get them to me within 2 weeks. So after 1 week, I will check on their progress. If they're falling behind, I will sacrificially take some of them and grade them as well to make certain that within 2 weeks, you all can get your full test grade. That is still well within. One of the most important things to me is that I make certain that you all have a good sense of how you're doing in this class before the drop deadline. Not that I want any of you all to drop the class, but the reality is, so where's the drop deadline? Withdrawal. March 24th. If you absolutely bomb and crash this first test, that is a bad sign, obviously. Obviously, that's a bad sign. And so that will basically take a discussion with me or kind of reflection, hey, do I think I'm going to be able to pull this back? So your first test is kind of your first big indicator of how am I doing. It's also my indicator of how I am doing. So it's a big deal for all of us. First test is always a big deal. But I will make certain to get those done with it, like get those graded within a couple weeks, get the full grade. But you'll at least know 60% of your grade pretty quickly. 60% of your grade being the multiple choice. Let's see. So yeah, on this one, you'll put your UCF ID and your name. Very important you put the UCF ID so I don't have to manually put it in. 220 grades takes a long time to put in. And that's why I'm giving the grader 2 weeks. Grading 440 free response problems takes a while. Ideally, they're putting in about 10 hours of work a week, so hopefully that's only 20 hours of work at most. But again, I'll check with them after a week and see how their progress is. So, that's the test coming up. We're going to do some review today. Our goal today, I looked at your all's responses to the poll. Thank you for the 28 or so responses I received. I put a handful of problems up here that kind of covered the main things I heard that were concerns were vectors. So we're going to do a problem on electric fields and vectors. It's electric forces and vectors. The same logic applies. How do you add up vectors? There's going to be a problem I'll do on the net potential due to a couple charges. I've gotten a lot of questions about that. And a conservation of energy problem. How to get the speed given a couple, given voltage and that kind of stuff. So, first off though, let's finish up that note card. Last class, and I posted this online. Last class I finished with the first 2 sections that we did, the first 2 weeks of content, plus our constants, plus our SI units. This week, we will finish up with the rest of it, which is electric potential energy and electric potential, capacitors and resistivity, and Ohm's law and P equals IV. So, let's go ahead and knock that out. So, we're going to start off with electric potential and electric potential energy. That's our next section. Ooh, this is not going to be fun to yell the whole time. Again, this is what it feels like to teach my high school class. So, I guess nothing new. So let's zoom on in. Boom, boom, boom. So this section is electric potential and electric potential energy. I'm going to put the units next to these. So electric potential. I want to remind you all that's V. V for voltage. That's another word for it. And electric potential energy. The unit for electric potential energy, it's energy. So the unit for it is joules. I'm going to put the units next to these because if you see these units in a problem, that indicates that this is the section you want to go to for the equations. The units kind of tell you what you're solving for and what you're working with. So one of the first things we introduced was the idea of potential energy. And we said that the potential energy, if you have a couple charges, so the potential energy due to 2-point charges was K, Q1, Q2 over R. This is a scalar. So there's no absolute values. You do need to put the positives and negatives here. The positives and negatives matter because it's a scalar, not a vector. So if I have 2 charges, doesn't matter what they are. Here's charge 1, here's charge 2. Charge 1, charge 2, and they have a distance. This equation gives me the energy that these charges have, the total energy stored in the system. How do I know it's stored energy? Because if I let them go, they're going to do something. So that means there's energy stored in it that when I let it go, it can do something, it can move. So that was our potential energy. And then we introduced the idea of what is causing this energy. What is causing something to have this energy? And just like things we have gravitational potential energy. What gives it this energy? How high up it is. How high up the thing is. So we introduced this idea of voltage. And we said that the potential energy is going to be, if I have some voltage and I have some charge in it, that's how much energy it has. So if I put a charge in some voltage, that's how much energy it has. Q times V. And then we kind of explored via that, how do you get a voltage? How do you generate a voltage? Well, in our problem up here, where we had 2 charges, I'm going to use the same picture, 2 for 1 duty. If I want to find the potential at some point, I guess I'll draw a different one. If I want to find the potential due to a point charge, what is the potential at some location? It is simply KQ over R. So say I have a positive charge, doesn't matter, some distance away, there's a point, and I want to find the potential there. That's the equation, KQ over R. The sign matters. Positive and negative matters. Because this is a scalar. When it came to vectors, you assign the positive or negative based on direction. Here, it's based on whether the charge is positive or negative. Okay? And then we said, great, you can get the potential due to a point charge at some distance away. We could also relate that to the field. But for now, I'm going to kind of riff off this. And I told you all that conservation of energy is very important for us to remember, that the energy initial, and I'm not going to even write E because I don't want you all to mix that up with electric field. Potential energy initial plus potential energy final equals kinetic energy initial plus kinetic energy final. And I was real kind to you all, and I basically let you know that every problem is going to, wrote that wrong. Potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. What you have in the beginning equals what you have at the end. And I was real kind and said if you rearrange things at the end of the day, they basically all boil down to this. Q times V equals 1/2 mv squared. If I give you the voltage, great, bam, plug in the voltage. If something is causing the voltage, for example, a point charge, say the point charge, say I put another charge here and I say how fast is that one going to fly away, then I got to put this voltage into this equation. There was a problem or two that we did like that. I did that in class with you all for a couple of them. So sad that these speakers don't work. All right, so we have that, and then there was one last equation in this whole potential energy business. Oh, actually, let's put something down here that's pretty important. We said that things want to go to lower energy. So I gave you all a hypothetical problem. I said, hey, here's 0 volts. Here's 5 volts. Here's negative 5 volts. And I said, hey, which way is a proton going to move? Which way is an electron going to move? Remember, everything wants to go to lower energy. Because the negative charge is negative, that lower energy is this way. Because the positive charge is positive, the lower energy is the other way. A negative number times a positive number gives you a negative. So this is actually a small value to it. Positive number times a negative is a negative. That's where the smaller area is. They both start at 0. And we're using this whole U equals QV situation here to say that it's going to lower energy. Spent more time on that. I'm not going to rehash that too much. But that's really important for us to remember. Which way do charges move in the presence of a potential difference? We previously talked about which way charges move. I hope I added that here. Let's see if Past Me did a good job. Yep. They move opposite directions when it comes to fields, and same thing here, they move opposite directions. That's why one's positive, one's negative. They're opposites. All right, last equation that's going to show up on here. Where do I want to chuck it? We said that the voltage equals the electric field times the distance. If you have a constant, you need a constant electric field. So pretty much the only constant electric field was due to a capacitor. But if you have an electric field and you have voltage and you have distance, bam, that's how you relate all three. So that's everything with voltage. It's a lot of things kind of going on here. But really the equation you need to remember are potential energy due to two charges, potential energy general form, voltage due to a point charge, conservation of energy, and the relationship between voltage, electric field, and distance. That bottom equation is a simplified one, only applies to constant electric fields. If the electric field was not constant, you would have to integrate. You don't have to worry about that. Okay? So I'll zoom out so you can see that if you're still copying that down. I'm trying to move a bit quicker because I want to give us time to solve these problems that I have set up. So that's electric potential energy. The next thing we visited was resistance and resistivity and resistance. What they are, and did we do capacitors at that point? Yeah. Resistors and capacitors. We talked about these. So right off the bat, we said resistance is rho L over A. A is the cross-sectional area. L is the length, so say I have a wire, boom, boom. That's the area, this is the length. Resistivity is a property of the material. It will be given. You do not need to know the resistivity of copper or gold or tungsten or whatever you may build something out of. I also gave you all the temperature coefficient of, I said resistivity depends upon temperature. That will not show up anywhere on the test, so I'm not going to waste space on this writing that down. That does come up on the quiz. You all saw that, but it's not going to show up on the test, so I'm not going to bother putting it here. I told you I'm not going to test you on it. Proved. It's not going to show up on here. I would not pull a fast one on you. All right, capacitors. This I will put the dielectric constant. It's not going to show up on the test, but you know what? Because it's not going to show up on the test, I won't put it. Whatever. Just so you don't get freaked out on the test and say, what's kappa? It's not given in the problem. Technically, there's a kappa in front. That's a dielectric constant. That makes your capacitor better. It's not going to show up on here. So again, I'm not going to bother with it. Capacitors. Boom. Two parallel plates. some area A, some distance between them D, and some charge. Actually, there's no charge here on this point. So, yeah.
So the unit for resistors is omega and then...
Ooh, that's good. Yeah, let's put that there.
And then the unit for capacitors.
Yeah, let me put that up here. Thank you for reminding me. Let's put those units up here because I said I would. So, where I did that in the last one. The unit for resistance is ohms, and capacitors is farads. So if you ever see farads in a problem, capacitors. If you ever see ohms in a problem, resistors. Now, resistors comes up in this and the next section, so there's a little overlap. All right, there's just a few more equations we need here. Thankfully, the week's kind of got simpler equation-wise as we've kind of gotten farther along. We need to remember that C is also defined as Q over V. And I'm going to put some little facts over here because I think this is important. Remember we had what stays constant when you have a capacitor hooked up, and there was kind of 3 different situations. So V constant if connected to battery. It gets the whole battery's voltage. So the voltage is constant if the capacitor is connected to a battery. Capacitance is constant if A and D don't change. Charge is constant if you charge it and then don't discharge it. If charged but not discharged. Okay? So these are the 3 problems we did. The 3 clicker ones, they're in the slides, but I think it's just, unfortunately, it takes a lot of space, but it is important to remember. If I order a capacitor from China, it's going to have the same capacitance even after it's traveled all the way across the ocean, unless it broke, which isn't great. So that's number 2. When it's connected to a battery, it keeps the same voltage. Who cares what I do to the capacitor? And then the charge, if I charge up a capacitor and I rip the thing in half, assuming I don't discharge it, which you probably will end up doing. But imagine you somehow don't. It's constant if charged and not discharged. Last equation that we need here is the energy stored in a capacitor. And here is where I'm going to point out something that is going to cause a very common mistake. The energy stored on a capacitor is 1/2 Q times V. All right? You may look at this and say, why is the teacher's pausing on this? If we look at the left side of our board, we have another equation that says potential energy equals QV. There's only one difference between these. This one has a 1/2, and this one doesn't. How do you know which one to use? If you have a capacitor, use that one. Otherwise, use that one. That's the really important thing. The energy stored on a capacitor. 4 capacitors, all caps. That's the equation. It's really easy to forget that 1/2. Or, it's really easy when you do the ones over here to accidentally add a 1/2. If you have a capacitor, use the one with the 1/2. If you don't, don't. All right, and we had 3 different forms to save you all some algebra headaches. We have QV, we have Q squared. I'm going to move this down a bit. The last section is going to be a little crammed, but that's not a big deal because it's literally 2 equations and that's it. All right. 1/2. And this is why I told you all you don't want to be making your note card at the same time as mine. I'm using all the space because I'm writing fairly big. I assume you all will be more efficient with your note card space. This is just to show everything's on there. I'd rather make it bigger so that you all can read it inside this room. In fact, I'm going to zoom in so you can read where the heck I'm writing. I need to make it big enough for you all to see. When you're doing the test, you can really zoom in on that thing. Okay. So there you go. That's the, very important. Let's kind of jot this down to the side. E is constant inside a capacitor. The electric field is constant inside a capacitor. And capacitor. Remember when I told you all that V equals ED equation? And I said the electric field has to be constant? Bam! Here's where an example where the electric field is constant. So, we've seen some problems with that. Okay, we have 2 more equations, and then that's everything. Good news is, if this feels like a lot, remember, if you see the word capacitor on the test, you go to this section. The other sections don't exist. When you see the word voltage, assuming it's not talking about capacitors, assuming it's talking about point charges, bam, you go here. If you see the word potential energy, you maybe have to decide, is it a capacitor, is it not a capacitor? If it's a capacitor, use that one. If it's not a capacitor, use the other one. So, the words and the problems will point you to the right section for the equations. All right, last section that's going to get crammed down here in this tiny little corner. Boop, 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 boop. We had current and resistance. Current and resistance. And this is very short. V equals IR. And then we have P equals IV equals I squared R equals V squared over R. Done. That's it. That's all there is to say to that section. Yeah, let's put those there. Thank you. Current resistance will still be ohms, but current is amps, and resistance is still ohms. I will remind you that the unit for power is watts. Let's jot that down there while we're. Current is amps, V is volts, resistance is ohms, power is watts. Okay. There you go. 5 weeks of stuff on one sheet of paper, effectively. So I will save this now in case anything devastating happens, so I don't have to redo it all. I will upload this after class, but I will upload it along with we're going to go ahead and do some practice problems. Yeah.
This was chapter 4, right?
Oh, yeah. That was, it was week 5.
That was 5.
Yeah, I think so. Let me double check. Yep. Resistors and capacitors is 4, and then current and resistance is 5.
So only those 2?
Yep, that's it.
Okay.
That's all we basically covered. V equals IR, P equals I, V equals I squared R equals V squared over R. There will not be any problems on the test about calculating how much it costs to run a light bulb. However, there will be one on the quiz. That's why I'm giving you extra time. See how I solved that last time? That's a useful kind of thing to know how to do. Knowing what a kilowatt hours is. Why am I doing it? Because you all have to, every single person in this room has to pay an electric bill. So it is one of the most applicable things that we've learned in this class. If you don't have to pay a power bill, bless you. But at some point you'll see it. So it'll show up one question on the quiz, but it's not showing up on the test. That's why it's not on here. Okay. So, just want to make certain, I think we're all pretty good. Again, I'll post these if there's anything in particular. We are going to start right off the bat with vectors, which is mathematically the most involved. Setting up the problem is actually not bad. The setup is quite quick. Doing the math is what takes a while here. But we need to be, vectors are important. You all spend a heck of a lot of time in Physics 1 working with vectors, so let's put that work to good use. If you don't know how to do it, that's why we're reviewing how to do it here. So it says find the electric force on the 3 microcoulomb charge shown below. Right off the bat, let's draw some arrows. So we are finding it on the 3 microcoulomb charge below. And remember, the way we do any of these problems, because we have a whole bunch of things going on, we just consider 2 at a time. So let's consider the effect of that negative one, that negative 6 microcoulombs on that positive one. Opposites attract. I'll draw up blue. So the force of this one is going to be in this direction, down towards the negative charge. And I'm going to label these. I'm going to call this one 1, 2, and 3, just so I can label this as F13. It'll just make it easier for us to keep track of what's what. So the force of the -1, which we call charge 3, on charge 1 is down to the right. Okay, then we find the direction of, we pretend like this one doesn't exist, the -1 doesn't exist, and we say, hey, what's that charge 2 going to do to charge 1? Well, opposites repel, like charges repel, so that's going to be up there. The length of my arrows is not significant at this time because I haven't calculated them, so I don't exactly know how big they are. So, for now, don't worry about how big these arrows are, just consider the direction they're pointed. F12 is real nice. That's going to be no problem for us. F13 is going to give us a little bit more difficulty. So, what is given in our problem? Let's go ahead and go through our steps. So, charge 1 is 3 e to the minus 6 coulombs. Charge 2 is 5 e to the minus 6 coulombs. And charge 3, I'm going to put the negative. It's going to end up, remember when we do vectors, we don't plug negatives into our problems. We consider which way it's pointed, and that determines our positive negatives, but for now we'll put the negative. We are finding the net force. The net force acting on charge 1 in this case. F net on charge 1. Again, I labeled these, so I'm going to call this charge 1. Just to clarify which one I'm doing. I don't care what's happening to the other ones. Okay, step 3. What equations are we going to use? Well, we're going to use the force on 2 charges, which is K, Q1, Q2 over R squared. Don't forget the squared, don't forget the squared, don't forget the squared. Force and electric field have that squared on the bottom. Voltage and potential energy do not. Again, that's also a classic mistake. It's accidentally squaring when you're solving for voltage or potential energy, or accidentally not squaring when you're doing force or electric field. Be very careful. That little 2 has been many a downfall, many a people's downfall. And then we got to get the net force. So we're going to have to add up all the x's, add up all the y's. So to get the F net, I'm going to kind of put that here. We're going to need to get the net x, which is going to be the x component of 1, 2, plus the x component of 1, 3. I left these both as positive. Well, x3, 1, 3 is pointed more to the right than it is. It's not pointed to the left at all. It's pointed to the right, so it's positive. So I'm already going to label that as positive. F13 is pointed more to the right. It's pointed to the right in some capacity. F12 equals 0. There is no x component of F12. I put it there just so you could see all the logic. But F12 is purely in the y direction. It's purely pointed straight up. There is no x component. So if you're confused why I was even writing it, I was just writing it to make a point that it doesn't exist. Now the F net y, that is going to be F12y. This is pointed up, so it's positive. F13 is pointed down, so it's negative. If you all look at the picture and you had to describe F13, hopefully you would describe that as pointing down, not up. So I make it negative because down is negative. Pointed down. Okay. All right, and I'm going to need a heck of a lot more space than this, so I'm going to copy and paste all this stuff onto another slide. Yeah, it didn't work the way I wanted to. All right, we'll copy all this over and attempt to move everything conveniently. For your all's free response, I think I already said this in class, but just to remind you all, I'm giving you a whole sheet to do that. The free response is not going to have that much space. The multiple choice is not going to have that much space, but I'll give you all scratch paper to work on for that. I give you lots of space on the free response since I'm grading you on that. I do not give you as much space on the multiple choice because I want to save paper. I printed out 220 copies. Any work you all want to do, I'll give you scratch paper you can do it on. And then you all can do with that whatever you want. But 220 copies times however many pages there are. You can see how that gets to be a big number real quick. So, I'll have scratch paper during the test. You're welcome to bring your own as well. Doesn't matter to me. Okay, so let's do the easy one. Let's get F12Y. F12Y is going to be very straightforward. That's just going to be K times Q1, Q2 over the distance between them. Let's call that R12 squared. K is 9 times 10 to the 9. Q1 is 3e to the minus 6. Q2 is 5 times 10 to the minus 6. And the distance between them is 2 meters. Where am I getting that 2 meters from? Bam. Right there. I'll go ahead and label that on the picture. This is R12, the distance between charge 1 and charge 2, which is 2 meters according to the picture. So that's a number. Our handy-dandy calculators. I think I've specified this, but just in case I haven't, you can use any calculator you want as long as it's not a phone. So bring your favorite. Okay? Nice and easy. 0.0338 newtons. And it's positive, so that means it's pointed up. Okay? Next one's going to be a bit more involved, and I'm going to literally spend a whole slide kind of breaking that one into components because I don't want to try to cram it in on this page. So F12Y, no problem. Done. F13, we got some work to do. And this is where our vector practice is going to come in. All those memories of solving problems in our Physics 1 class. So let me draw. Again, I'm going to basically give a whole slide to this. So getting F13, you know what? Let's just, no, I'll do it over here. I'm going to redraw the picture. I'm only going to draw, I kind of have to draw all of it. Draw. I'm just going to copy it. All right. Make it a little smaller to give myself, it doesn't like that. That's fine. All right. I am trying to find the X and Y components. So this is F13. Charge 1, charge 2, charge 3. I'm going to draw that arrow over here. I'm going to redraw that arrow over here because we got to do some geometry. Trigonometry, in fact. If we look at our picture, no angles are given. We need to solve for one of these. We need to solve for an angle. Let's do this one. It's right next to it. Why not? We're allowed. How do I get that angle? Boom, there's a triangle. So let's get that angle first because we're going to end up needing it. What is given in the problem? SOHCAHTOA, y'all. SOHCAHTOA. If I have a triangle, and this is my theta, hypotenuse, opposite, adjacent. SOHCAHTOA. What numbers do I have in this problem? I have 3 on the bottom and 2 on the side. So I have opposite and adjacent. Process of elimination, TOA is the only one that has an O and an A in it. So that's what I'm going to use. Tangent of theta equals opposite over adjacent, which is going to be 3 over 2. If you're solving for theta, that's going to be tangent inverse of 3 over 2. Your calculator makes certain you can have it in degrees or radians. It does not matter as long as you're consistent. And that comes out to 56.31 degrees. There you go. There's an angle. We're going to need that. Why are we going to need that? F13 is very straightforward. Getting F13 is, well, okay, I say straightforward. We also need this distance. We'll call this the distance 1, 3. So let's get that distance as well. How do I get R13? R13 is going to equal the square root of 2 squared plus 3 squared. It is the hypotenuse. A squared plus B squared equals C squared. R13 is the hypotenuse of this triangle. I know the bottom side. I know the left side. So I square those. I add those. And if this is any encouragement, y'all, if a problem like this showed up, it would be a free response. There's no way I'd give a problem like this as a multiple choice. Because look at all the steps you're having to do. And take heart, you get partial credit on these things. So, if this was a problem, and you set up all this kind of first part right, step 1, step 2, step 3, that's 12 points out of 20. The other 8 points is doing the vector stuff correctly. So, take heart when you're looking at this if you're intimidated and like, oh my gosh. Remember, partial credit's a thing. All right, so that equals 3.61. Great. So now that I have all this, if I want to get the force of 1,3, that's going to be K Q1 Q3 over R13 squared, which equals 9E9 times 3e to the minus 6 times 6. I should have done this before. When you all are doing this, I put this in the note sheet. These are absolute values. Absolute values, because remember, we assign the positives and negatives based on the vectors, not based on the... We've already done the work with the positives and negatives. So when I'm plugging in these numbers, absolute values. Should have specified that. When you're doing vectors, the charges all get absolute values. Which just means the negative doesn't matter. 3.61 squared, this is a number. 9E9 times 3e to the minus 6. I'm saying it out loud so I don't make a mistake when I plug it in. 99 times 3e to the minus 6 times 6e to the minus 6 divided by 3.61 squared. Don't forget the squared. Double check that what I plugged in is what's on there. It is 0.12 newtons. All right. We got to get the x and y component. We got to get the x and y component. So, how do I get the x and y component? We look at our triangle here. Here's my F13. Here's my angle. The x component is the bottom side. The y component is that side. SOHCAHTOA, y'all. SOHCAHTOA. This is where this may not make you happy. Maybe you're not happy at this point anyway, whatever. But you all remember from Physics 1, often that the x component was cosine. But let's look at cosine here. Cosine up here. Adjacent and hypotenuse. Which of my sides is adjacent? And I'll even label it here for y'all. The adjacent is the y component here. The opposite is the x component. That's okay. That's not a bad thing. That doesn't mean we did anything wrong. That just is why it's not always cosine for the x component. Sometimes it is, sometimes it isn't. It depends what side is touching your angle. Here my y side is touching my angle, so that's cosine. The x side is opposite it. So when if I want the x component, it's going to be F13 times sine of theta. If I want the x component, or the y component, it's going to be F13 times cosine of theta. All of that, if you don't know why, this triangle holds all the secrets. The y, in fact, I can kind of put that up here. If I call this F13, that's Fy, that's Fx. That's just how it worked out in this problem. Okay, so and I wrote that number wrong. 0.012. So 0.012 times sine of, we already got the angle before, 56.31. 0.012 cosine of 56.31. Boom, 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 boom. This one's going to be 0.00999 newtons. This one's going to be 0.00. Well, that's kind of unfortunate. All right. Sorry for any, just so no one gets wigged out. There we go. We'll put an extra decimal place so it's not spooky. All right. Great. At this point, y'all, we get to assemble the things and find the direction. We got our F13X, we got our F13Y, we have the F1 thing before, we can put it all together, make a nice little pie. This is the most mathematically challenging problem that can show up on the quiz, or the test. And if this happens, here's my recommendation, y'all. Do it last. If you know a problem is going to take you a while, make it one of the last things you do so that you can spend your time on things that take less time for you to get more points. Test-taking strategies is use your time efficiently and effectively. Use your time where you get the most points. So, if this was a problem and you're like, all right, I need to do this, maybe just do steps 1, 2, and 3. Spend your time on other problems that you feel like you could be more efficient and then come back to this. That may be an option. It would be very bad if you spent half your time on one problem that's only worth 20 points out of the 100. That's not an efficient use of time. So, test-taking strategies. All right. And I am writing this out slowly and surely, so it's also taking me a bit longer. And this one was gross. This one's angle was not nice and pretty. We had to actually find the angle, so it involved a bit more work. A reminder to you all, when I solved these problems myself to see how long it would take you, the most time it took me to do a free response was 8 minutes. Clearly, this is taking me more than 8 minutes. Okay? So, shows you the level of complexity that may be expected. All right, so Fnet equals the Fnet x. We already wrote this. In fact, I'm going to steal it from my other one so I don't have to rewrite it again. All right, so plug and chug. Let's grab the other one as well. F12y equals 0.0338. F12x didn't exist. So F2net x equals 0.00999. Done. This one equals, we take the number that we did before. This is one from our first slide. 0.0338 minus 0.006656. F12y we solved in the first slide. That's where I got that number from. F13y I got right here. That equals a number. We're on the home stretch, y'all. .0271 newtons. All right. At this point, if you get to this point, that's pretty good. We're not quite done. We're so close. So close. I need to get Fnet. How do I get Fnet? Square root of fx squared plus fy squared. To get the net, I got to square these things and add them together. So 0.00999 squared plus 0.0271 squared equals a number. All right, 0.1035. Now, this tells us the amount. It does not tell us the direction. So there is one last step we need to do. It's not going to be super long. We just got to find the angle. We got to find the angle this is pointed at. How do we do that? We draw those vectors and make a triangle. X is pointed to the right. It's positive. Y is pointed up. So tip to tail, tip to tail. I'm going to go ahead and label these. 0.00999. Oh, sorry, that's not the right number. No, that is the right number. 0.0999. This one is 0.0271. We just found the net vector. That goes right there. I want this angle. SOHCAHTOA, y'all. SOHCAHTOA. Pick whichever one you want. Sine, cosine, tangent, who cares? I prefer to use tangent. Tangent theta equals opposite over adjacent, so you don't need the net force for this. You can just use the ones you already have. So theta equals tangent inverse of opposite over adjacent. If we look at my angle here, what's my opposite one? That one, 0.0271. What's my adjacent? That one on the bottom, 0.0099. I'll label those. Opposite, adjacent. So that's just theta equals tangent inverse of 0.0271 over 0.00999. Long story short, if you want the angle, you just tangent inverse y over x. That's always going to be true. If you ever want the angle, tangent inverse y over x. That one does hold true. 0.00999. 69.76 degrees. Nice. There you go. And I feel like no, that's good. Okay. A lot of work. I wrote every single step, which is also why it was a lot of work. If this does not make sense, please look over this, review this, practice your vectors, practice breaking the x and y components. I know I didn't spend a ton of time practicing vectors in this class. Why? Because you all spend a heck of a lot of time in Physics 1 practicing it, and in this class they only show up in the electric fields, the force due to electric fields, and when we eventually get to magnetic fields. So, because it's not the first time you all are hopefully seeing this, I'm not spending a ton of time on it. That's why I didn't have a ton of practice problems with this, whereas your Physics 1 class did. All right, we will have plenty of time for the rest of these because they won't take us long. So don't worry there. So I'll leave this for a few more moments, and then we'll get on to some potential ones and some ratio problems. Choo. All right, two charges, 35 microcoulombs and negative 50 microcoulombs fixed in place. You know what? Let's change some numbers here. This is the exact same problem in your problem set, so you probably already solved it. So I'm just going to change the numbers because I'm allowed. Whatever. Same logic's going to hold. Two charges. Let's draw a picture of it. I got a lot of questions about this one, either through the survey or through email. So that's why I want to spend the time on it. Here's charge 1. Here's charge 2. Q1, Q2. It says they are a distance 0.1 meters apart, and I got rid of my unit, which wasn't great of me. Where is the location where the potential equals 0? All right. Step 1, what's given? Q1 equals 10 e to the minus 6. Q2 equals negative 60 e to the minus 6 coulombs. And the distance between these two, R12, equals 0.1 meters. What are we solving for? You have a choice. You can either have the distance from charge 1 or the distance from charge 2, where V net equals 0. Finding where the place where voltage equals 0. Where is that magical location? Okay. It's going to be somewhere between these charges. It's going to be somewhere between these two charges. We're going to hope that these numbers work out. I'm a little worried. Depending on how, let me make this number a little bit bigger, just so I 100% know the problem will work out. It will work out, but it'll change. So I'm going to make that 0.8, because I realize there is the potential that everything could get a little dicey. All right. What equations do we have? We want V net to equal, so V net equals V1 plus V2, and that's going to equal 0. Our net, that's what the problem is saying. Where does the potential equal 0? What's my variable for potential? V. What's the equation for V's? V equals K, Q over R. So I find each potential, I add them up, they should equal 0. That's how I'm going to find my location. Now, something to note here is that, remember, the signs matter. Notice I didn't put absolute values. We also, we'll do it when we start solving it. Let's do it when we start solving things. So V1 is going to equal K Q1 over R1. Pretty straightforward. V2 is going to equal K Q2 over R2. I'm not going to put in any numbers yet. Remember, I like to leave out the numbers as long as possible. Put that in the equation. So V1 plus V2, so K Q1 over R1 plus K Q2 over R2 equals 0. As it stands, we cannot solve this problem because R1 and R2 are both unknowns. If you have two unknowns, one equation, it's a no-go. You need one unknown, one equation. So this is where we're going to use that. R1 plus R2 equals, let's change that, 0.8. That same strategy we've used for like 3 different problems now. We know the point's going to be somewhere in this thing. It's going to be farther. It's going to be somewhere closer to this. If this is R1 and this is R2, they have to add up to 0.8. This plus this is that. So we've used this strategy now like 3 times for 3 different problems. So pick your poison. I'm going to solve for R1 because who cares? And we're going to go ahead and plug that in. So K Q1 over 0.8 minus R2. And I'm going to go ahead and kick the other one to the other side. Collapse some steps in here. Write it a little bit nicer because it's a little crammed down there in the bottom. I just kicked the thing to the other side. I subtracted, if you're wondering what step I did here, 1, I replaced R1 with this, and 2, I just subtracted that over. Why did I do that? Because it makes it easy for us to recognize that the K's cancel. Saves us a little bit of effort. All right, we're going to need another slide, and we'll be able to knock the rest of this one out. At this point, it's just algebra. We know Q1, we know Q2, one unknown, math. This would also be a free, like if this is a hypothetical, basically all these long ones, if it's taken me more than 5 minutes to solve, that's going to be a free response. I'm not going to give you all a multiple choice that takes a long time to solve. Multiple choice problems should take you at max. So to give you a sense, I wrote out every single step when I was doing that timing. When I was timing myself and seeing how long it took me to do it, I was writing everything out. I was not skimping on things, trying to hold things in my head. And the multiple choice questions, I finished all 25 of them in 18 minutes. That's not me bragging how quick I did it. That's letting you know that if there was a lot of writing, I would not have gotten it done in 18 minutes. That's why it took me 8 minutes to do the free response. I was writing out every single step because I wanted to accurately, you all I assume will hopefully write out every single step. So I wanted to account for that time. All right, so let's just copy and paste this jazz over to this one. So we're going to steal just this last step. We'll steal everything. We got the room. It's not that big of a deal. At this point, y'all, it's just algebra. There's nothing too fancy. The physics is done. So we still have that negative. So now we're left with Q1 over 0.8 minus R2 equals negative Q2 over R2. And you may look at this and be like, oh no, a negative. Remember, Q2 is negative, so it's going to cancel that out. Okay. At this point, kick all the R2s to the top. Pro tip in algebra, if you have a variable you want and it's on the bottom, get it out of there. Get it to the top. So I'm going to multiply the bottoms to the other side. So I have Q1 times R2 equals Q2 times 0.8 minus R2. There's a negative in here as well. I'm going to go ahead and bump that Q2 to the other side so I can get my constants together. Let's move the negative as well. Why not? I'm allowed. And now it's just plugging in numbers. I mean, I guess I can plug in the numbers. I don't know how much that benefits us necessarily. 10e to the minus 6. Let's make everything a little smaller so I don't. All right, 10e to the minus 6 over negative 60. There's that negative sign in front. There's that negative sign there. Those two negative signs will cancel, which is great for us. Those e to the minus 6s will cancel. R2 equals 0.8 minus R2. So I get 10 over 60, which is just 1 over 6. R2 equals 0.8 minus R2. 7, add the R2 to the other side. 7 over 6 R2 equals 0.8. R2 equals 6 times 0.8 divided by 7. I'm rushing through this last math steps because at this point, I'm not really teaching you all too much here. It's just algebra. How do I get R1? I just do 0.8 minus that. I'm not going to look. I'll write down R1. I kind of ran out of room here. R1 equals 0.114. Bam. I just did 0.8 minus that from our original equation right here. R1, 0.8 minus R2. So 0.8 minus that, bam, done. So what's the takeaway from this problem? Net voltage, add up the voltages. What's the equation for potential? KQ over R. If you understand those two things, if this was a free response, you get most of the points. You need to know how to add up net voltage potential. You just add up KQ over R, put the right numbers in all day. So it's nice and scalars, no vectors, no x components, no y components, so the math was snappy. The concepts was a little bit longer. Maybe. Okay? 2 more. Basically, I'm going to do a potential energy and then just a bunch of ratio problems. The ratio problems, these are great multiple choice questions because they don't take that long to do. Whereas all of these where I'm having to write out a bunch is that. So let's go ahead and knock out this potential energy one. Ooh, I didn't put enough information here. What voltage is necessary to accelerate a 3 microcoulomb charge to a speed of 50 meters per second? I didn't put enough information here. I will actually, this is a great teaching opportunity. Let's see what variable I should have given you, and I'll add it once yeah, let's explore what variable I also need to give you. So, 1, what's given? Q equals 3 e to the minus 6. Again, I am straight up telling you there is not enough information to solve this problem. I made up this problem very quickly. I can make up a number for it just as quickly, so I'll do that in a second. Don't worry, you can solve every problem on the test. How do I know this? I went through and solved every problem on the test, so I know for sure that you can do it. What are we solving for? Voltage. Now, remember, every time, if you see the word speed in a problem, velocity, speed, conservation of energy, done. Like, automatically, your brain should go to conservation of energy. That's the only way to solve these problems. There is literally no other way I've taught you. You would technically need calculus to do it the other way. All right, what's my equation? Conservation of energy. QV equals 1/2 mv squared. All right, hopefully you can see what variable that we need that I didn't give you. It's mass. So let's make up a mass. Give me a number. I don't care.
49.
There you go. Good choice. M, the mass of the particle. Let me move all this stuff down. The mass of the particle is 3 grams. Ooh, just to be mean. Remember, grams is one of the weird, mass is one of the only metric units that likes having 2 letters. So the mass here is not, yeah, sure, I could put 3 grams, but that's not good. I want kilograms. That is 3e to the minus 3 kg. If you're converting from grams to kilograms, 3e to the minus 3 kg. It's minus 3 because a gram is smaller than a kilogram. So that's one way to remember this. should I make it positive 3 or negative 3? 3 grams should be a very small amount per kilogram. That's the way I remember. When you are doing this, you're like, oh, which way should I go? Should I make this 3 e to the 3 or 3 e to the negative 3? 3 grams is small. My answer should be small. If I put 3 e to the positive 3, that would be 30,000. So that's good, though. That's a great question. All right, plug and chug, y'all. I'm going to go ahead. Again, I told you I like to do things in terms of variables. So QV equals 1/2 mv squared. Let's just solve for V. That's going to be, I'm going to rewrite this a little different, and it's fine. I just divided the Q to the other side. You may wonder, why is that 2 on the bottom? Because that's the same as 1/2. 1/2 is the same as dividing by 2. That's a little more concise to write it that way. But if you really want, multiply by 1/2 out front. Either divide by 2 or multiply by 1/2. Same thing. Plug and chug, y'all. So this problem is actually not too long. Again, it's longer. This is maybe borderline multiple choice. There wasn't actually that many steps, but the multiple choice, if there's math you're doing, it's basically just one equation. It's a one-step problem. This is kind of a one-step problem. You just plug everything in, done. Finding the force due to just 2 charges, plug it in, done. All the multiple choice would be just basically one-step problems. The free response is where things can get spicier. So the multiple choice you can kind of think of as any problem from like the first half of a problem set section. The free response would be from that latter half where the problems get more involved. 1.25 e to the 6 volts. Okay, I'm going to double check that I plugged that in right. There you go. Beautiful thing about multiple choice is if you get an answer that's not one of mine, that's a great indicator that you did it wrong. So there is some niceties to multiple choice. There is the downside, it's all or nothing. So why isn't my whole test free response? Time. I know where it's time and breadth. Multiple choice lets me ask more questions and see more things that you understand. Free response lets me test the depth of your understanding better. Depth versus breadth. Trying to balance the two. Okay. Let us close this out, and probably the last bit of class will be kind of just answering any questions you all may have, because we're running pretty good. We'll see. We'll probably end up with just 5 minutes off or something. All right, what happens to the force between 2 charges if I triple the distance between the charges? Ratio problems. I see the word force, so I go to my section of my note card that says force. And I realize, oh, the force due to point charges is K Q1, Q2 over R squared. That's the equation for force. And this says what happens to it. So this is my OG. This is my original. Nothing's changed. Then something does. Spend a few seconds. What variable is changing? K, Q1, Q2, or R? Spend a few seconds actually thinking about that. All right. Which one? R. Now, here's where if we make a mistake, here's what's going to happen. So Q1's the same, Q2's the same, R is changing. R is tripling. Here is where you may make a mistake if you make a mistake on this. You need to square that 3 as well. Because, make up numbers if you all want. If my original radius is 1, 1 squared is 1. If my new radius is 3 times farther away, 3 times 1 is 3. 3 squared is 9. You can see how we have to square that bottom. So let's go ahead and square that 3 now. So that's going to be 9r squared. We pull that 9 to the front. And we got to keep it where it's at. If it's on the bottom, it needs to stay on the bottom. Bam. What happened to my force? It's 1/9. Okay. Be careful with distance. If I tell you the charges are changing, that's much simpler. You just chuck it in front, pull it to the front, good deal. The distance is kind of the trickiest version of this I could give because you got to square what happens to it. We've done a few of these. But if your variable is squared, whatever changes to it is also squared. If your variable is squared, whatever happens to it is also squared. That applies to any problem ever. So my new force is 1/9, the original. So if I call this one F1, it is 1/9 F0. Let's say F0 is my original. My new one is 1/9 that. Kind of crammed in there, but you get the idea. Every ratio problem, every problem like this, you do the same way. You find the equation, you find the variable that's changing, and you just put that number in front of that variable, pull it all to the front, combine when you need to, and solve. So we'll just do the next two, and you'll see I'm going to do the exact same process. What happens to the capacitance if I double the distance between the plates? We see the word capacitor. So we go to our capacitor section. What equation for capacitance has distance in it? Epsilon naught A over D. So whatever these problems are, you go to, if it says capacitor, go to the capacitor section. I say I double the distance, find the equation with distance in it. So that's my original. What's my new one? What's changing here? Area is the same, distance is doubling. You just pull that to the front, same thing. It's on the bottom, stays on the bottom. Equals 1/2 epsilon naught A over D. Boom, it's half the original. All these ratio problems, the process is the same. The only trick to it is finding the equation and then putting the right multiple in front of the right number, and if it's squared, make certain you square that change, like we did in the first one. But the process is the same. And we're going to keep doing ratio problems like this, so they should hopefully get easier and easier as you get the strategy down. All right, this last one I was a little mean, because I changed 2 variables. Oh, man. So then we just got to do that to both problems. I'm going to give myself a little bit more space, because I know this one's going to take a little bit more space. All right. What happens to the resistance if I double the length and half the radius? Spend a few seconds. See if you can find the equation that has resistance, length, and radius. I will tell you, it probably won't say radius in it, but it may say area, which is based on radius. So see if you can find that equation. What's the equation? I mean, this is what you'll have to do on the test anyway. What equation has resistance, length, and radius? It's not going to show up as radius, it'll show up as area. Anyone find it? Starts with a row. Anyone know what comes next? There's an area on the bottom, length on the top. This is our equation for the resistance, given length, the material, the area. I'm going to rewrite this so you all can see where that radius comes in. Pi r squared. Remember, every wire, every resistor we work with, we consider as a circle, a circular wire. Say circular wire. A tube. I don't know if you all have ever seen a wire that's a square, but I haven't. So you basically consider every wire in this class, every resistor, as a cylinder with a cross-sectional area. That's a circle. All right, so that's my original. Let's do our new one. Our new one has a resistivity. I double the length and I half the radius. Remember, if the variable is squared, whatever happens to it is squared. If the variable is squared, whatever happens to it is squared. Just like that first one, which is now very hard to read. All right, we got a few moments. Try to pull those numbers to the front. I set it up for you all at this point. Square the 1/2, pull the 2 to the front, pull that squared 1/2 to the front. See if you all can get what that number is that's going to pop up in the front. Because at the end of the day, I need some number times R naught. So you need to pull that 2 to the front, square that 1/2, pull that to the front, combine them. Try it. Spend a few seconds. See if you can get the right answer. Because it's one thing to set it up, it's another thing to get those numbers correctly. And fractions on the bottom can sometimes trip people up. That's normal. So just to do one more step, pi times 1/4 times r squared. So hopefully you got 1/2 squared is 1/4. I'm going to kind of slowly do each step because I want you all to see if you can kind of do this. Pull the 2 to the front. That 1/4 is in the bottom, so it needs to stay in the bottom. 1/1/4 times rho L over pi r squared. So there's our R naught at this point. And so it's just a matter of what's 1 over... Heck, plug it into your calculator if you need to. You all have a calculator, so if you're not confident in your ability to like mix around those things, use a calculator. Why not? You got it at your disposal. Use every tool you all have. 1/1/4, keep flip change. Keep flip change. That's going to end up being just 2 times 4. Times R naught, 8. So if you got 8, awesome. If you didn't, that's okay. You got to practice, try out these kind of things. Make up your own numbers. Make up your own numbers. Say what happens if I third the radius or fifth the radius or whatever you may want. Apply it. Look at this as kind of a reflection for it. So, hey, look at that. We do have 5 minutes. Normally I don't like to end early, but because you all are paying for this, but I'll reserve the last 5 minutes for kind of like individual questions you all may have about anything. This covered the vast majority of things I saw. Look at the clicker questions. Look at the problem sets. Email me if you have questions. I will do the best I can respond. I will do the best I can to respond to them in time. And my encouragement to you all, this test does not reflect your ability as a person. It just reflects if you understand the stuff we covered in a physics class. So I'll repeat that because a lot of people put too much stress on themselves with these things. This test is just testing if you know physics. It's not determining your whole future. Just one test. Yeah, what's up? The only difference... Oh, I guess I should have this true. Goodbye, online people. If you have questions, ask them to me through email.